All right, we are live. We got Steve in the house. We got Jason in the house. Thanks for joining in and welcome to another, so we're going to continue our mastering ampacity discussion. Hopefully, yeah, I'm getting audio. All right, so Steve, feeder OC, let's see what Steve's got to say. Hold on. Let's take a look. Feeder OCPD, 250 amps, 250 kc mil conductors with 4 gauge equipment grounding conductor. Jason, happy Fused Friday, everybody. Absolutely. Oh, yes, Maggie is doing good. She has had her surgery, so we're back from that, and I do believe, yeah, I do. I've got a... I guess I don't. All right, thought I would be able to share a picture, but I can't. In any case, thanks for asking, Jason. She had her surgery. They put a plate in. They fixed her knee. They also didn't have to remove a portion of her tail. They took that little tumor off, so that was good. We have a great set of doctors out there at Ohio State University. Dr. Dice was the doctor that operated on Maggie, and he did Jake's first surgery as well. Really good guy, and the whole team out there is absolutely awesome. So can't say too much more. I mean, that team in Ohio State University, the vet group, is top notch. So very happy with how that came through. And Maggie's walking on her legs. She's over there right now. That's why I'm in my kitchen, because I can't go downstairs. Bobby Joe's going to head out around 12:30, something like that. So I got to be here to watch my girl, make sure she doesn't try to hop up on a couch or anything like that. Okay, but thanks for asking, Jason. And I'm missing tonight is our dinner at NTI. John McCamish and Jerry O'Connor are heading up to NTI as we speak. They're driving up to Michigan. Unfortunately, I am going to miss it. Unfortunately. Santiago Guzman, great to see you today. Hey, my friend. Hopefully you are doing well. And everybody down there is healthy. I hope the little bambino is doing good. Joe Bellantoni, good morning. Hey, you like the shirt, huh? It's Friday. So it is Friday. And Jorge, can we say as a rule of thumb that the ampacity of the wire must be larger than the circuit breaker size? Not necessarily, Jorge, not necessarily, and I'll give you some examples why in a second here. But that I would say not necessarily. Trying to figure out my iPad here. Boom. Okay, there we go. All right. So let's do this. Jorge and crew, I just want to give you a sort of an update on where in the slide deck. First things first, I am reconsidering. I'm not going to throw it away yet, but I'm cautious. And I'm concerned about using the term circuit ampacity. I know the whole point of this one slide in the very beginning was to establish that there's a difference between the conductor ampacity and the limitations placed upon the circuit by the termination or the equipment, not the conductor, right? Because the conductor will have an ampacity based upon conditions of use. That doesn't change. Ever. What changes is when I landed on a 75° C piece of equipment or a 60° C piece of equipment, now that conductor that has this big ampacity value, I can't use all of that ampacity because I'm limited by the termination rating. And I need to really... Yeah, circuit rating. Ooh, I'm going to put that, maybe circuit rating. I'm thinking about it, Jason. That's not a bad idea. But so I've got to think. I got to think of a new term there. And I also put a note over here that the term conductor. I had an interesting discussion with another gentleman. We were talking about conductor, and he said, you know, the term conductor is not a defined term. 210.19. 210.19. You know what I don't think I can do? I don't know. I'm going to try this. I'm going to try something. 210.19. Oh, I can. Okay, I can. 210.19. So he's mentioning 210.19. So if I go to 210.19, conductor minimum ampacity. Yeah, so the term conductor is not a defined term. And I was talking to Jeff Sargent yesterday about, I kind of remember somewhere in the code cycle, the term was going to try to be defined. His thought was it was back there in the data side of the business. But in any case, the term conductor is not defined, but we do have a definition for device and equipment. So we should be able to differentiate between the conductor and the equipment. I'm just pointing that out. And then I'm changing. Remember, Jason, I was talking about the circuit ampacity just up above. And I mentioned that I wasn't sure I liked that term, right? But if I kept it, let's say we kept circuit ampacity, I had to remove conductor out of it because it's not about, so how I would define it would be the maximum amount of current in amperes that a circuit can carry continuously under specified conditions of use. And I'd almost want to take that out. I'm going to put a strike through with that, and I'm going to highlight that red. Just bear with me. In amperes that a circuit can carry continuously without exceeding the equipment temperature ratings. So I'm going to get rid of the conditions of use because conditions of use only apply to a conductor's ampacity. The termination has a 75, say it's a 75 degree C rating. I go over to the 75 degree C column and I use that number and I say that device or that equipment with that size conductor can handle that much current continuously, right? So I think if we created a defined term of circuit ampacity, which it's growing on me, but I still have this concern of using the word ampacity because it's a defined term and it has conductor in it. But if I use the circuit ampacity and say the maximum amount of current in amperes that a circuit can carry continuously without exceeding the equipment temperature ratings, that is, I think, the essence. Whatever the term is, that definition is the essence. Hey, Brian Rock. We never did connect, Brian. I missed your phone call. I can't remember what was going on, and but we're going to have to connect sometime. Hopefully you're doing well. Brand circuit rating is the, yes, I agree with you. Jason says, I agree, the conductor should not be a part of it because the conductor will have an ampacity that is not the same as the, oh, you're exactly right. Now, it could sometimes be identical. In fact, there was one example that I did where the conductor ampacity and the temperature rating in that 75 degree C column equated to each other. And in that case, that presented some challenges on how to describe when you can go to the next higher and when you can't, but we're going to get to that. So I'm going to try to fix that. Right, so let's do this. I'm gonna save a Rev 8 file, save as, and I'm gonna save this as a Rev 8, and I am going to get rid of this text, and I'm gonna get rid of this text. Boom. I'm going to get rid of this. And I'm going to get rid of that. I still don't know if I like that, but I like the way this is going. All right, Santiago, my good friend. Should this definition include the consideration of motors? Oh, okay. So Santiago, oh, I like what you're saying. So I had this discussion. I had this discussion yesterday with an individual, with another gentleman as we were talking about this. All of this discussion right now in this journey of understanding ampacity is focused on feeders and branch circuits. I haven't hit services yet because services presents another challenge, and I haven't hit motors yet. Once we hit services and once we hit motors, I may have to go back to this definition of circuit ampacity and make a modification. I agree with you. I think I agree with you. But as we get there, so I like what you're thinking. I like where your head's at. I agree with you that that could impact the definition of this. So thank you. Excellent. Oop, take that out. Hey, we got Dawn Gannier in the house. Thanks for joining in, Dawn. Okay, so I made that change a little bit. I tweaked that a little bit. I'm going to delete this because what I'm doing here is I'm pointing out the fact that we're going to take this out. I'm pointing out the fact that equipment is a defined term, right? And the definition of equipment is including fittings, devices, appliance, luminaires, apparatus, machinery, and the like as part of or in connection with electrical installation. And a device is a defined term, and I would say a circuit breaker is a device. And Santiago says, and also the terminal's temperature limitation. Ah, yes. Yeah, you're right. Now, here's the challenge, Santiago. I can have a piece of equipment rated 75 degrees C, and I can put a lug in there that says 90 degrees C. But that doesn't mean I can use a 90 degrees C conductor at its 90 degrees C ampacity. That just means that that lug, that termination, is a 90 degrees C termination, but the overall equipment is still 75 because when we test an assembly, we're looking for the overall temperature rise in that enclosure, and even if I have components in there that are 90 degrees C, the assembly itself is still 75. So I agree with what you said. The terminal's temperature limitation, that may be a bigger number, but or it could be a smaller number, and I could have an issue with having to go down. But if my equipment is 75 and my terminal is 90, I'm still limited by the weakest link, which is the overall equipment, overall assembly. Man, thanks for joining in, Santiago. You are the man. Okay. All right. So I just put a note in there, and what I could do is I could also define that there is a term there's a definition for devices as well. All right. Yep. The terminals, Brian Rock in the house. Terminals thermally conduct to adjacent insulation. Absolutely right, Brian. Okay, so I made that slight change. Now, when I left off, if you recall, when I left off our last discussion, I had an example. I can't remember where it was. It's one of these examples. I've done so many examples since last week because I needed to really wrap my head around this discussion of 110.14 versus 310, the conductor ampacity versus the equipment capabilities, right? I'll call it a rating, or the limitation to the circuit due to the equipment. So I've done a lot of homework, and if you recall, when we were talking last, we had a situation where we said I could go to the next higher in 240.6b. I think it's 240.6b or 240.4b. Hold on. Is it 240.4b or 240.6b? 240. I want to read this because this caused me a lot of 240.4b. Overcurrent devices rated 800 amps or less. And I tell you, this was, I've been struggling with this one because the challenge here is whether or not, when I'm in the 75°C column because of the termination, can I go to the next higher? And at face value, when this first came up, I was, if you recall in that video, if you watched towards the very end of the last week's session, I sort of hesitated. I said, well, wait a second. Somebody said, well, you can go to the next higher. And I'm like, well, I can't go higher than the termination. I can't go higher than the equipment rating. And then they referenced 240.4b, and then they said, oh, no, you can because of 240.4b. And then I pointed out the fact that in 240.4b, let's see if I can do this. I don't know if this will work. No, see, it's not going to work. I don't know why it doesn't do that. Anyway, in 240.4b, the language says the next higher standard overcurrent device rating, and it says above the ampacity of the conductors being protected. And that's where I hesitated, because the 75°C column use is not the ampacity of the conductor. The ampacity of the conductor is always based upon the conditions of use. Because if you look at the definition of what, and I have it in my slide deck, I have the definition of ampacity in my slide deck. And we pointed this out right at the beginning of all of our discussions. It's the maximum amount of current in amperes that a conductor can carry continuously under specified conditions of use without exceeding the conductor temperature rating. So when I look at 240.4b, it says the next higher standard overcurrent device rating above the ampacity of the conductor. It doesn't say the ampere rating of the termination. It says the ampacity of the conductor. Not the circuit breaker, not the equipment. Those are defined terms. So I can't, if I'm using the 75°C column, I can't go to the next higher. And I will, and I confirmed this with the product standards on how we're tested. And I'm going to go through that because I wanted to make sure that I was 100% accurate in how I'm portraying this, because when I go online, I see examples that use the 75°C column. They go to the next higher when it doesn't equal a standard ampere rating overcurrent device. And that would be incorrect. I threw an example out on Facebook and LinkedIn, and there was only a couple people, Jason, you were one of them, that got it correct because of this minor little detail. And it's a mistake that, I mean, I know I made that mistake in the past. So I'm going to go to that example. What was that example? That example was, I got to go to my Facebook page. Whoa. I know it was on Facebook and I did it on LinkedIn. let's go down and take a look at the example. The example said, what size feeder overcurrent protected device and conductor is required for 184 amps? So 184 amps. I did the example in here, 184. There it is. Okay. All right. Let's close that. And let's go back here. Boom. Okay, so this was the example. And remember, and I feel so solid about this process. Yeah, Jason, 184. So I feel so solid about this process. I've verified the results back over to UL standards, UL 98, UL 67 for panel boards, and UL 489 for circuit breakers. And I'll show you where there is 3 areas where we have a discrepancy. Okay. What size feeder overcurrent protected device and conductor is required? I'm using THHN, so that's 90 degrees C. Insulation is required for 184 amps of continuous load on a panel board, 75 degrees C terminals, equipment. The conditions of use of the conductor are 3 current carrying conductors in a raceway in an ambient of 86 degrees Fahrenheit. So it's all standard stuff. I'm not adjusting for conditions of use. If I go to, I drew the picture out, right? So I've got 184 amps continuous. Everything is 75 degrees C. I need to determine the conductor size and the overcurrent protected device. And based on the requirements, I have to do 2 calculations. I have to determine the size based only on 125% of the continuous plus the non-continuous. I have to determine the size based upon the conditions of use, and then I select the larger of the 2. The 1.25 times 184 is 230 amps. If I do the conditions of use, which align with table 310.16 conditions of use, I'm using the value out of 310.16, which is no multipliers against 184 amps. So if I have 184 amps of load, I'm not adjusting it for temperature. I'm not adjusting it for the number of conductors. I have 184 amps. I'm going to use 184 amps. The larger of the 2 is the 1.25, so I pick a 230 amp circuit, right? So now I know my ampacity of my conductor has to be greater than or equal to 230 amps, all right? So that's my 230 amps. So now I go down and I go to my table 310.16 and I pick the 3/0, and I'm going to use the 90 degree C column because I have 90 degree C conductor, THHN. And I'm applying it in a way that I can leverage the 90 degree C insulation. It is 260 amps. So I'm at a 4/0 conductor because that is the next one higher. So I selected and I said I got a 4/0 conductor up here. And you know what to do? I'm going to highlight that as burgundy, just so we know we just selected that. The conductor ampacity at 90 degrees C is 260 amps. I'm going to say the equipment 75 degrees C. The equipment, I'll call it a rating. Jason, I like your use of the term rating. The equipment rating or the circuit ampacity at 75 degrees C is 230. All right, so is equal to 230 amps. Okay. All right, so 260 at the conductor ampacity. The equipment rating in this case is 75 degrees C, so the equipment is limited to 230 amps. I'm just threw that in, right? So now we've satisfied 1, 2, and 3. We have selected a conductor that has an ampacity value greater than the larger of the 2 calculations. So, so I'm doing circuit ampacity. I went back to circuit ampacity, 75 is 230. So now the third step, what's the third step? Evaluate the selected conductor per 110.14 to ensure the termination in the equipment, right? So now I have the lowest temperature rated equipment is 75. Both ends of the conductor are 75. The 90 degree C ampacity value is not able to be used for this application because it's limited by 75. And I like what Brian said. Good luck finding a piece of equipment that's rated at 90. The maximum current for this circuit will be based upon the 75 degree C column of 310.16, which is that 230 amps. A 4-aught copper conductor in the 75 degree C column is 230 amps. 230 amps is greater than 184. So I can carry the load with 230 amps worth of conductor, or actually the ampacity of that conductor is greater than that, right? The 90 degree C column is 260. So the conductor itself can carry 184 amps. The equipment that's rated 75 degrees C with a 4-aught landed on it can handle 230 amps continuously. So the equipment can handle the load amps of 184. The conductor can handle the load amps of 184. I'm good on both cases, right? And you'll notice what I'm trying to do is I'm separating the discussion. I have the conductor ampacity. I'm going to treat it separately. I have the equipment limitation, the rating. I'm going to treat it separately. Both of the numbers, the 75 degree C column and the 90 degree C column, both of those, and based upon the conditions of use, the conductor ampacity, both of those values are greater than the load amps of 184, I'm still good, right? I'm good at this point. And then what I'm showing you here is the 4-aught 75 degree C and the I'm going to copy this, Control C, I'm going to move this down here. So what I'm showing here is the 90 degree C ampacity value of the conductor, 4-aught, and I'm showing the 75 degree C equipment. And you know what I did? And I didn't do it here, but I'm going to do it. I'm going to do it right now. I am going to insert a shape, and I am going to hide all of these things here. I'm going to shade this out as white because we don't care. We don't care what the insulation rating is of this conductor, right? I'm using the 75 degree C column, not because of the insulation. And this used to confuse me when I worked for a consulting engineering firm when I came out of college. I could not understand why I was using the 75 degree C column, which had conductor insulation values in there. If I read that column for 75, it says a type RHW, THHW, and I would tell the PE I was working under, I have a THHN, I can't use the 75 degree C column, and he'd say, ignore that. I'm like, well, I can't ignore it, it's right there. I can't use the 75 degree C column, I have to use the 90 degree C column. And he said, no, you're doing this because of the equipment, and I did not understand that, but I blindly followed the rules. So I'm hiding those conductor insulations because they have absolutely nothing to do with the equipment itself. This 230 amps has nothing to do with the conductor ampacity. The conductor ampacity of a 90 degree C THHN 4-aught conductor is in these conditions of use is 260 amps. It can handle 260 amps all week, all day, all night, okay? The termination and the equipment can't handle 260 amps. It can only handle 230. It has nothing to do with the conductor. It doesn't change the conductor ampacity. It changes the circuit, what the circuit capacity is, but it doesn't change the conductor at all. All right, so now I've settled all four. I have a 4-aught conductor. I have checked the circuit ampacity, the termination. I have checked the ampacity of the conductor. Both of those exceed the 184 load amps. The continuous current is 230 amps. Now I'm going to get into selecting the overcurrent protected device. And thank you, Steve, for joining. Thanks for joining, buddy. You're the man. Welcome to the discussion and our journey of mastering ampacity. Okay, so the continuous current, 1.25 times 184, which is going to be a very important number only for selecting the overcurrent device. I don't worry about 1.25 times 184 on the equipment rating. I don't worry about 1.25 times 184 for the conductor ampacity. I worry about 1.25 times 184 for the circuit breaker, because it has to be greater than that based on Article 240. James Smith, welcome to the program. Good to see you, my friend. Thanks for joining in. Welcome, James. All right, so in this case here, 240.4, we already did 240.4. Yep, we did that. Okay, so I got to change that text. 240.4b, overcurrent devices rated 800. Okay, so now 240.4b tells us that I can go to the next standard overcurrent device rating above the ampacity of the conductor. So that tells me for the conductor ampacity at 90 degrees C of 260 amps, if I want to protect the conductor, I can go to the next higher, which is a 300 amp. The standard ratings is what you have to go to, right? So I would go to 240.6, 240.3, 240.6. And if I have 260 amps to protect the conductor, I could go to a 300 amp overcurrent protected device. Okay? So to protect this conductor at its ampacity, because of 240.4b, I can go to a 300 amp and it will still protect the conductor. Not the termination, but the conductor. Right? Because it says above the ampacity of the conductors. It does have conditions for the use of that. In this example, we cannot use the next higher standard overcurrent device above the ampacity of the conductor because I have to protect the equipment at 230 amps. The weakest link is the termination, which is only 230 amps. Okay, so that takes care of 240.4b. All right, and that's a very important take care of 240.4b, because 240.4b only applies to above the ampacity of the conductor, not the termination, not the equipment. All right, so now I go to 215.3, because this is a feeder. Overcurrent protection requires that feeders be protected against overcurrents in accordance with Part 1 of 240. The feeder supplies continuous loads, etc. So we already know that. We know that the overcurrent device must not be less than the non-continuous load plus 125% of the continuous load. That's the significance of 1.25. So I know that I can't have an overcurrent protective device less than 230 amps. It's got to be greater than 230 amps. So that's a criteria, piece of criteria. All right, so select the overcurrent device that protects the conductor at its ampacity and is not less than the non-continuous load of the 125%. The overcurrent device must not be greater than the circuit ampacity. So I can't, if I go greater than 230 amps, I'm not protecting the equipment at its rating. The equipment tells me it's tested for 75 degrees C. I've got to make sure that I have to protect the equipment at its rating, which is 230 amps. If I put a 250 amp breaker on here, I would let 250 amps of current flow through a terminal that's only rated for 230. That would be ungood. Okay? So I've got to make sure that my overcurrent protected device is less than 230, and the next one down is what? 225. So I can protect the circuit at 225. A 225 amp breaker will protect the conductor at less than its ampacity, which is 260. So I have more conductor than I have terminal. And but a 225 amp breaker is not greater than 1.25 times 184 amps. So I have a problem with that. Now, I can't just increase my 225 to 250 because now I'm not protecting the equipment at 230. So the only thing I can do is increase the size of the conductor. So there's the numbers. There's your 290 for, I went to 250. So if I increase it to a 250 from a 4-aught, now my conductor ampacity based upon conditions of use is 290. My equipment termination, which is 75 degrees C, is 255. And let me do this. I'm going to do this, Control C. I got to do this because I tell you what, I don't know about you, but for me, those insulations confront. We have taken 1.25 as a rule for OCPD, but it's only the maximum overload, meaning we could select between 1.1 and 1.25 for the OCPD. On the motors, so I think what you're saying is on motors, Santiago. And and you might be right on. You're probably right on motors. I have not done motors. Is going to be another portion of this journey through ampacity. All right, so 75. So that's my 75. So now, if I come back and I put a 250 kc mil, my conductor ampacity is 290. My circuit ampacity, the 75 degree, my equipment can handle up to 255 amps. My continuous current is 230. Now I can select a 250 amp circuit breaker or fuse, and it will be less than the circuit ampacity. It will be greater than the 230, and I'm protecting the conductor at its ampacity. So now I have a 250 amp overcurrent device. I gotta make this white. I have a 250 kc mil, Maggie, no. I've got a 250 kc mil conductor, copper, THHN. I have 184 amps of continuous current. Shh. 184 amps of continuous current. And I just got to watch Maggie. Maggie, lay down. Lay down. Lay down. Sorry. Lay down. Maggie, lay down. Good girl. Okay, so I got a conductor ampacity of 290. I got a circuit ampacity of 255. The 250 protects the equipment because it's less than 255. The 250 protects the ampacity of the conductor because it's 290. And it is greater than 1.25 times 184. So now what I do is I go to, and this is an important piece of it. You've got to make sure, or I did a verification. How do we test a circuit breaker, a 250 amp circuit breaker? And then how do we test panel boards? Now, a testing of a panel board will follow the rules in 489 for a molded case circuit breakers, and fuses are the same way. But I'm going to use a circuit breaker as the example. If I go to 489, there is a table in 489 called Table 6.1.4.2.1, Terminal Current and Conductor Size. The terminal current, that's the rating of the breaker, so the long time pickup. For a 250 amp breaker, we test it with a 250 MCM conductor. That's how we test it. I can't go smaller than a 250 MCM on that breaker because that is how it's tested. If I put a 4-aught, if I go to a 4-aught on a 250, I would be misapplying the circuit breaker. And if I'm misapplying the circuit breaker, when I put it into an assembly, I'm going to exceed the rating of the assembly. Same thing for fuses. No different. They use the same table. They use the 75 degree C column. So the 4-aught on a 250 amp breaker is a misapplication of the breaker. A 250 MCM, and we got there because we followed the rule. And the rule was, my overcurrent protective device has to protect the 75 degree C column. It's got to be less than what's in the 75 degree C column. It has to be greater than what the continuous current, 1.25 times continuous plus the non-continuous, and it's got to be less than or equal to your conductor ampacity. Thank you, Jason. I appreciate it. What's Brian saying? Maximum terminal temperature rise, delta T terminal has to be less than the temperature rating of the wire insulation, maximum ambient anticipated. I would agree with you. Awareness of the separation of the conductor, equipment, and circuit ratings. Yes. So that's, Jason, for me and the way I think, I've got to separate the discussion. I've got the conductor ampacity, and that's always going to be what it is based upon contingent conditions of use. I can push that conductor however I want to. And if I want to land it on a 90 degree C lug and terminal and then go to a larger conductor to come down to the breaker based on 75 degrees C, I can do that. The temperature, the ampacity of the conductor doesn't change. Just because I landed it on a terminal of 75 or 60, the conductor ampacity doesn't change. The limiting factor, I'm not going to use all of the conductor ampacity. I'm only going to use what the weakest link will let me use, which is the equipment or the termination, right? So, okay. So, let's do another example. Let's go down below. I'm going to go down below. I did a few other examples. Here is this was 180. What was that one? I think I did 186. Let's do 180. Let's walk through, let's walk through 180 amps of continuous load. I'm going to pick the conductor size and I'm going to pick the overcurrent device. Both of these are 75 degrees C. Remember, I'm going to do 1, 2, and 3. I'm going to do 1.25 times the continuous plus the non-continuous. I'm going to do the conditions of use. Remember, the 1.25 has to do with the equipment. It has nothing to do with the conductor itself. The conditions of use is the conductor. The 1.25 is your equipment, pretty much your overcurrent device and your 80%, right? So the 1.25 deals with where the conductors are landed, right? The conditions of use is the ampacity of the conductor itself. That's what's going to dictate what the conductor can handle. Whichever one is greater, then that's the size, that's the number I use when I pick my conductor ampacity. So the 180 amps times 1.25 is 225 amps. The conditions of use, I match what's in 310.16, so I don't have any multiplying factors. And I'm at 180 amps. Be quiet, Maggie. 180 amps. I calculated 225 and I calculated 180. 225 is the larger of the two. She's so frustrated. 225 is the larger of the two. So, why did I say that? Hold on. I didn't finish this one. We're going to do this one together. 225 and 180. 225 and 180. The larger of the two is 225 based on the current, based on the continuous current calculation. Sorry for the spoiler. All right. You have 4-aught on a 225. All right, let's see if you're right. So I've got 90 degrees C of 225. So I pick a 3/0, okay? So look at this, a 1/0, a 3/0. A 3/0 conductor has an ampacity for THHN insulation of 225. Okay, and I'm going to do this, bam. And then I come down and I say a 3/0 conductor, 225 yields a 3/0 copper conductor with a THHN insulation. So not a 1/0, but a 3/0 is selected to meet the requirements of 2. Okay, so now I've met one. I've met the conductor ampacity at its insulation. So now I'm going to say, okay, now I've got to think about the termination. So I've got conductor ampacity 225, circuit maximum is 200. Let's make sure that's right. 200. You be quiet, Maggie. 200, 310.16. 3/0, expand table, right? I'm at a 3/0 conductor. 3/0 conductor is in the 75 degrees C column is 200. Is 200, 75 degrees C, 1.25 times 180. So now I know from this, I know my overcurrent device can be 225. My circuit, I have to have an overcurrent device for a 3/0 less than for 200 or less. So a 200 amp breaker would work, but my 1.25 is 225. I've got to be equal to or greater than it. So I could do a 225. Maggie, shut up. I can do a 225, but I can't because of that. So, Jason, I'm going to have to increase the conductor size. Let me see, 3/0 conductor, 225, 3/0 conductor, 225. Based on this, it has a maximum of 200 amps. Based on this information, 180 amps is less than the ampacity, so all of that is good. There's my numbers. There are my numbers. And now I'm into selecting the overcurrent device. There's my 225, 200, 225. I'm at the 3/0. I make sure I got all the right numbers here. 215, all this good stuff. So those are my code references. I come to this one and I say, okay, 240.4b permits the use of a 225 amp breaker, so I can protect this conductor at its ampacity, which is 225. It matches a breaker size, so I can't go to the next higher. I can use a 225 or smaller. 110.14c requires the OCPD to be 200 amp circuit breaker, right, to protect this or smaller. But 215.3 is not met because 200 is not greater than 225. So now the conductor size will have to be increased from a 3/0 to a 4/0. And then I go to a 4/0. Now my conductor ampacity is 260. That means I can go to a 300 or 275. 275. Circuit maximum is 230, which means I can do a 225. And my 1.25 is 225. So 240.4b permits the use of a 300 amp circuit breaker. 110.14c requires the overcurrent device to protect the equipment at its 75 degree C rating, which in this case is 230. A 225 amp breaker will provide that protection. 215.3 is met because a 225 amp breaker is equal to or greater than 125% of the continuous current plus the non-continuous. And now I go to UL 489 and we say I have a 225 amp breaker, and look, I can put a 4/0. I can't put less than a 4/0. I can put bigger than a 4/0. But now that selection aligns with exactly with what is in UL 489. A 225 amp circuit breaker, a minimum conductor size is 4/0. The selection of OCPD and the conductor sides aligns with the 75 degree C and aligns with the UL standard for 489, which will align with UL 67, which will also align with UL 98 for switches, etc. Okay? And that completes it. So, let's talk a little bit more. Hold on, Salas, Salsa. Is there an NEC requirement that dictates choosing to protect the conductors versus the equipment? 110.14. So let's do this. Let's go back. I'm going to go back to the very first example. The very first example, and Salsa, Brian is 100% right. 110.14c, you have to protect the weakest link. In some cases, the weakest link is the termination. If I have a condition of use that puts the ampacity of the conductor less than the termination, I have to protect the conductor, and that overcurrent device to protect the conductor may be less already than the termination, but I may have to bring it lower to protect the conductor at its ampacity. And I'll be able to go to one step higher in that case. And I would argue that I believe this example did it. So let's go back to the first example that I did. The first example was 4 current carrying conductors, 120 degrees Fahrenheit ambient, and the conductor has to have a 90 degrees, and the conductor has a 90 degree C insulation. And I have 88 amps, and the reason I picked 88 was because of Back to the Future. Okay, if you're a Back to the Future fan, 88 miles per hour, I think, was the speed he needed to get the DeLorean up to get into the future. Mr. G, excellent. He's a salsa lover. Mr. G, thanks for that clarity. Okay, so let's go to this example. We're going to do the process. We're going to calculate the load current at 125%. We're going to calculate the load current, I'm not going to say load current. Calculate the current using only the conditions of use. And then select the larger of the two. So let's do that. So, this is 210.19a. So 88 times 1.25 is 110. Okay. And when I do the conditions of use, remember I've got 4 current carrying conductors. So immediately I'm doing an 80% multiplier. On the ambient temperature, I was 120, so now I'm at 0.82. And I do this because I have a 90 degree C insulation. Now, if my conductor was only 75 degrees C insulation, I would do my factors off of the 75 degree C column. So keep that in mind. I know we default to 90 all the time. And we'll always say, oh yeah, you can just do your multipliers off the 90 degree C column. That's only if the conductor itself has a 90 degree C insulation. If it's a 75 degree C insulation, then you have to use the 75 degree C column. Hey, Willie Snyder, happy Friday. So, and remember, a THHN is not always 90 degree. If I'm in a wet location, and where do I find that? I go to, remember, I would use 310 dot, is it 310? There's a table in here. 310.4, pin header. I'm going to look for THHN. THHN. Where is THHN? I know you're in here somewhere. Yes, I do. All right, so THHN is always 90 degrees C. I was thinking of THHN, dry and damp locations. But what about a wet location? It has to be a THHN-W or -2, I think, or THWN. THWN is 75 degrees C and dry and wet, and it's THNW-2. So there was one in here I saw that had a split rate. There it is here. XHHW. If you have XHHW, it's 90 degrees C in dry and damp, but it's 75 in wet. So you have the same insulation rating, you just got to be mindful of how you're using it. So in any case, I'm using 90°C column. For a 120 degree Fahrenheit, I do a 0.82 multiplier. So now we're going to do the ampacity. Now, we divide by these numbers to increase the load. If I was going to use these multipliers in table 310.16, I would multiply these multipliers by the ampacity to bring the conductor ampacity down. So what I'm doing here is I'm taking the 88 amps and bringing it up based upon these multipliers, which will make me use a larger conductor, which would be the same as taking that larger conductor and multiplying it by 0.8 and multiplying it by 0.82 and bringing its ampacity down. So 6 of one, half dozen of another. This is just an easy way to do that. So I take 88 over 0.8 times 0.82, and I get 134.15. So now, the larger of the two is not the 1.25 times the continuous. The larger of the two is the 134.15, which is based upon the conditions of use. So now I'm driven off of that. So now I've got to find a conductor with an ampacity equal to or greater than 134.15. In the tables, I would pick a 1 gauge conductor, which is 145 amps. Okay? So now I'm at a 1 gauge. Now I've got to go through, now I've satisfied the first step, right? I've satisfied the calculating the two numbers, pick the larger of the two, select the conductor that meets that requirement. So now what I have to do is take the 1 gauge conductor and do the rest of the evaluation for 110.14. So now I say I have a 1 gauge conductor, and I'm going to do this. I'm going to put these numbers in. We know the conditions of use already. So 1 AWG copper ampacity. I'm just going to do this. Ampacity. Ampacity at 90 degree F, 90 degree C equals of a 1 gauge. I'm going to close this. I'm going to come over to 310.16. Maggie, lay down. 310.16. Where is it? There it is. Lay down, Maggie. 310.16. Expand. Pin. I have a 1 gauge, so I know I'm at 145 and 130. Lay down. 145 and 130. So 145 and 130. Ampacity is 145 amps. And then I know, I'll call it the circuit ampacity at 75 degrees C is equal to 145, and was it 130? Yep, 130. 130 amps. Continuous, 1.25 times 88 amps equals, was that 110? Was it 110, guys? Yes, 110. I'm here, right? So 110. So I've got my numbers. I know that I have to be less than or equal to 145. So 125 amp breaker is standard. I have to be less than 130, but I have to be greater than, ooh, this looks pretty decent, doesn't it? So I'm going to copy this, copy that, Control C, and I come down to, we already said there is your 130. I didn't have to go over there. All right, delete, Control V. The continuous load is 88. The ampacity of the conductor based on the conditions of use is 145 amps. 145 base times 0.8 times 0.82 is 95.12. The conductor can handle that current indefinitely. So the ampacity of the conductor is 95.12 amps, right? That's right. Ampacity is not 145 amps. It's 95.12 amps. So I got to fix that, 95.12 amps, because that's got to be based upon the conditions of use. I can't just use the 90-degree C column. Ampacity is 95.12 amps. All right, so I fixed that. I come down to this, 95.12 amps, so I can go to a 100 amp breaker, right? So with 95.12, I can go to a 100 amp breaker and protect this conductor at its ampacity. The 130 amp circuit ampacity, the 100 amp breaker would be less than 130, but a 100 amp breaker is not going to handle 110 amps, 1.25 times the continuous. So that mix doesn't work, right? I can't go to 110 amps because 110 amps won't protect the conductor at its ampacity. 110 amps will protect the circuit at its ampacity, but it's not going to protect the conductor because the code 240.4b only lets me go to the next higher for the conductor ampacity, right? So a 100 amp circuit breaker is not going to work. A 110 amp breaker with this 1-aught conductor is not going to work. So I said a 1 gauge conductor terminated on this equipment can carry up to 130 amps continuously based on the 75-degree C column. Based on this information, 88 amps is less than the ampacity of the conductor. Yep. And hence we have the requirements of 110.14. So 110.14 is met because all I have to make sure is that the continuous, now I have to pick the overcurrent device. Okay, so the conductor ampacity is 95.12. Is that right? Yep. Equipment ampere rating is 130. Okay. And here's what I'm going to do is I'm going to do this. I'm just going to copy this, Control C, and I'm going to bring this down here to Control V. All right, so now I've got my 95, I've got all the data. I know my overcurrent device has to protect the conductor at its ampacity. 210.20 requires the OCPD to be at least equal to non-continuous plus, et cetera, 125%. 240.4b lets me go to the next higher OCPD for this application size above the ampacity of the conductor, right? So, boom. A 100 amp breaker, we just said 100 amp breaker would be permitted based on 240.4b. 210.20 requires the OCPD to be at least equal to the non-continuous blah, blah, blah. So we said that's not going to work. 100 amp breaker ain't going to do it. 1,000 points of light. So now I've got to increase the conductor to a 1-aught. When I increase the conductor to a 1-aught, the conductor ampacity is 111.52 because I have to take the 90-degree C column, 170 times 0.8 times 0.82. So the conductor ampacity is 111.52. I can go to the next higher for the conductor. So that tells me I can put 111, I can put 100 and, what's the next higher? I don't know why, I always have to do this. I got to go to 240. Here's what I like to do. I go to 240, right mouse click, open a new tab. I come over to here. I click on 240.6. Go to 240.6, standard ampere ratings. All right, expand. Okay, so I'm at 111.52. My next standard higher is 125. So I could put a 125 amp breaker on that. Or I could have put 110, because a 110 amp breaker would protect that conductor at its ampacity as well. 125% of the continuous current and will protect that 1-aught conductor at its ampacity. So a 110 amp breaker is greater than 125% of the continuous. It'll protect the equipment. Let's do this. I'm going to take this out. I'm going to go back up to here. Hold on. Where did I have it? Right here. Do this. Control C. So this is 150. So I can delete that. So I have a 1-aught conductor. Control Z. Right, the ampacity for the 1-aught is 111.52, which is 170 times blah, blah, blah. Circuit ampacity is 75 degree C column, which is 150. And then 1.25 times 88, which is 110. So I could say down here, a 110 amp circuit breaker, OCPD, satisfies all of the above, right? I could also say a 125 amp OCPD satisfies all of the above because 125 amps is the next higher, larger overcurrent device over 111.52. So this is an example, Salsa, of your question of the limiting factor, okay? So now, let's go do this. I can put a 110 amp breaker or 125 amp breaker. I could do either up here. That could be either a let me do this white, bam. 1-aught conductor, THHN, and I'm going to do this. Oh, and there's the conditions of use. 4 current carrying conductors, 120 degree ambient, 90 degree C insulation, 88 amps load. That now let's do this. Let's go to 489. I have a 1-aught conductor, and the question is, can I protect the larger of the two? Can I protect a 1-aught conductor with a 125 amp breaker? 1-aught conductor with a 125 amp breaker. Let's bring over UL 489. This is UL 489. What was the amp breaker? Jeez, oh man. 125 amps. 125 amp breaker. So let's 125 amp breaker is right here. And I can put a 1, which I'm at a 1-aught, so I'm 1 up. I can't put a number 2, I can't put a 2 gauge. I can put a 1-aught, I can put a 1, but we already tried the 1. The 1 didn't work because, hold on. Oh, the 1 didn't work because I couldn't put a 125 amp breaker on it because of the ampacity. The ampacity was of a 1 gauge with the multiplying factors was 95. I can't go to 125 amp breaker because I'm limited now by the conductor ampacity. All right, so, all right, let's do this. I am going to come back and let's take a look at some questions. I know I had some stuff. Yes, oh man, Zacapa. It's downstairs. I got the Zacapa XO too. Good rum, and I'm looking forward to seeing you again. I I was surprised the 10 amp circuit only lasted one cycle. What do you mean only lasted one cycle? 10 amp circuit's still there. It hasn't gone away. Not sure what you mean, Willie. Salsa, this is why the NEC is so great. It regulates the whole beach all the way down to the grain of sand, generally down to granular. Yes, and you know what, Jason? The challenge is applying it and reading the terms. I think that 110.14 could be written better. I really do. And I'm going to write some language. Happy Friday. Mr. G, excellent. So Salsa, perhaps this next observation I'm going to make is off topic, but I believe it has relevance. Lifespan of the insulation of conductors. Ooh, so here's my thought. Salsa, Mr. G. That's a tough question. Lifespan of a conductor. Insulation. I think if you apply it correctly, if you apply it within its limits and you don't exceed the temperature ratings in a controlled environment, I mean, you look at homes that have been wired. Now, I know that some older wire can get brittle. I've got some knob and tube. The insulation's still working great. I don't know the answer to that question, Salsa or Mr. G. I really don't know the answer to that question. Wait, why use Ampacity at 93 if the equipment is rated 75? Wouldn't you have to use the 75? No. So the Ampacity the 90° C column. You're like my straight man. Ow. Dadgummit. I hurt my knee. Ouch. So, oh man, my knee. If I go to I think it's 110.14. 110.14 tells me in C, there we go. It says it right here, Bryansky. It says that, I'm going to read right here. Conductors with temperature ratings higher than specified for termination shall be permitted to be used for ampacity adjustment, correction, or both. So what we're doing in our examples is we're going to the 90° C column because it's a 90° C insulated conductor. If it was 75° C, I'd have to use a 75° C column. But if it's a 90° C insulated conductor, I can use the 90° C column for adjusting the ampacity of the conductor. I don't have to use the 75. I know you know that. And thank you for being my straight man. All right, we got friends, long lost friends joining each other now. Give me a call sometime this evening, Mr. G. All right, PM me your number. I'm still unpacking my new... Oh, what part of Florida did you move to? You thought CAM 70-106 prohibited the use of 10 amps. Oh, no, it doesn't. And I'll tell you why, Willie. Here's why. If you go to... How do I do this? If you go to 310, let me show you something. If you go to 310, so two places, two things I will tell you. 310.5 is ringing a bell. Is it 310.5? No, it's not 310.5. 310, where's it at? Oh no, I'm sorry, 110. 110. Let's go to 110 dot, maybe it's 110.5. Yes, I knew it was a .5. If you look at 110.5, Willie, 110.5 says conductors used to carry current shall be of copper, aluminum, or copper-clad aluminum unless otherwise provided in this code. It says if the conductor material is not specified, the sizes given in this code shall apply to copper conductors. Read the next sentence. If other materials are used, the size shall be changed accordingly. So, for example, if we put this in, what section? So whenever you see, so let's do this. Let's go to dum, ba-dum, bum, ba-dum. I'm going to do this. I'm going to go to the section. What was the CAM number? CAM 70-106. So let's look at 70-106. I'm glad you brought that up. 70-106, NFPA 70, 2026 code. CAM 70-106. Let's go to the CAMs. There we go. Oh, look at that. It goes right there. So I should be able to see this. Boom. So Control F, 70-106. And do it again. Do it again. All right, so what it says the minimum size of conductors for voltage ratings up to and including 2000 volts shall be 14 AWG copper and 12 AWG copper-clad aluminum, or 12 AWG aluminum, except as permitted elsewhere in this code. So if I go elsewhere in the code, and let's say you go to, I don't know, chapter 2, 210, like we permitted the use in chapter 2, we permitted the use of a 10 amp circuit. So, 240, no, I'm sorry, 210 dot, branch circuit, is it 20? 210.20, overcurrent protection. Equipment outlet devices, nope. Where's the, oh, no. 210.20, what was 210.20? 22? Nope. We've got a minimum size, but we just say 12 AWG, which would let you use, what's the next higher, 14 AWG? So because of that language that says unless elsewhere permitted, that doesn't really do it. So that's why their CAM, Crystal Hunter, who was the submitter of that CAM, put in an appeal because what she wants is all of these other areas to be fixed, because they did that over in 310, but it doesn't apply everywhere. Because if you specifically say, hey, if for example, you said you can use a 14 AWG as the minimum conductor size, then you can, because of the language in 110.5, you can adjust the size based upon the different material. So it didn't go away. It's still live and kicking. All right, let's go down through here. So, Brian Rock, if you don't exceed long-term temperature, then forever. Yeah, that's right. I agree with you, Brian. Tom Sebastian. Whatever that means. Greetings, Willie Snyder, 210.16. 210.16. Maybe that's where it's at. 210.16. Oh, wait, that might be in the new edition. www.fpa.org/70next. You lay down 210.16. If I go to second draft, it's going to ask me for my password, and I'm going to go to 210.16, 210, chapter 2, 210.16. There is no 210.16. I think that says 16. Or is that 18? No, it says 16. There's no... Oh, 18. 210.18. Branch circuits recognized by this article shall be in accordance to the maximum permitted ampere rating or setting of the OCPD. Yeah. So 210.18 is a good example where we say branch circuits rated 10 amps shall not supply receptacle outlets. So that's one example, Willie. And now we don't recognize a copper-clad aluminum or copper. We just say we permit a 10 amp branch circuit, and we do that in various locations in 210. All right, so Brian Rock, yep. Oh man, I'm hoping I get down to Arecibo. I'm hoping. Ah, Sebastian, Florida. I thought you were talking about a person's name. Okay, so let's get back to our discussion here. So, with regard to mastering ampacity, where are we at? We're at 1252. So, I feel comfortable with the branch circuit and feeder. With the equipment 110.14, and 110.14 and all that jazz. Now, I am going to share with you an analysis that I did. Maggie, no. I'm going to share with you an analysis that I did on UL 489 because there is a discrepancy. Maggie, no. Jeez, oh man. She is persistent. Lay down, girl. She's got that bad leg and she's trying to push through a barrier. So here's what I did. In UL 489, I took a look at the table that's in 489, and they'll tell you the number of conductors. They tell you the copper conductors for 75 degrees C. They give you a 60 degrees C as well, but I just focused on 75. These are the values from 310.16, the 75 degree C column. And this one here is D3 times B3, which is that 310.16. Maggie, she got through her barrier. Lay down. Good girl. She just wanted to be over there. 20 and then 75. Okay, so I don't know why I didn't do this one, but this looks at each of the circuit breaker sizes and it compares the circuit breaker rating with the total amps. So in this case here, I have a 40 amp breaker, I have one 8 gauge, and an 8 gauge at 75 degrees C is 50 amps. So the breaker is less than the 75 degrees C column. And I did that all the ways down. And you'll notice it is the case, except for, now for a 400 amp breaker, we test typically with 2 3/0. And I've got to double check, but I'm not sure why this is the case. But for some reason, on a 400 kc mil, a 400 amp circuit breaker, The two 3/5 3/0s, I've got a 1 o'clock meeting. The two 3/0s equals 400, which is fine, okay? And that's where this is okay. But they permit me to put a 1 500 kc mill, which is only good for 380. You'll notice all the ways up, all the way down, up through this 400 amp test, they permit this 500 kc mill on a 400, and now it violates the rule. I don't know why yet, and I am investigating that. I had talked to Jeff Sargent a little bit. I spoke with a few people who have been on the UL 489 standard in the past. The closest I can come to is they'll tell me that they believe it's related to the service conductors and service conductor sizes being used for 500 kc mill, 1 500 kc mill being landed on a 400 amp service. I still have to do some homework. Dawn Gannier, you're probably the better person, even a better person that might know a little bit of that history. But I don't understand why I can put a 500 kc mill at 380 amps ampacity on a 400 amp breaker and violate the rule. And it's in the UL standard. The other two locations are a 3000 amp copper and a 5000 amp. So both, and it's just on a 3000 amp, I can use 8 500 kc mills, which is 3040. The breaker is less than that. I can use 9 400 kc mill, which is 3015. The breaker is less than that. But I can use 7 600s, and that's 2940, 60 amps less than 3000. I can use that, but it's less than 3000. I don't know why. Same issue, and I'm looking at copper right now on 5000. I've got 1, 2, 3 options. One of the 3 options, 13 500 kc mills at 4940, is less than 5000. So I have 3 instances on copper, and I've got 3 instances on aluminum. Again, I don't know why that abnormality exists in the standard. I'm going to research that though. But Dawn Gannier and others out there who have been probably doing this and have been noodling around in this area might have some good history there. But I would appreciate that. A piece of utilization equipment draws between 2 and 5 amps during its operation, but at the start it draws close to 16 amps. I've seen some electricians use a 14 gauge, but shouldn't that be a 12 gauge? I can take a look at that next week. I've got 2 minutes to my next meeting. Yeah, Maggie wants to help me on my live chat. Yes. She does. She's laying right there. Ampacities were added in T310.16 for 16 gauge copper and 14 gauge copper clad. Yes, they were. So it's in 310.16 as well. Excellent. So Dawn, this is one I would love to get your research on, because I don't understand why in all of these conductors, every single one of them, I have the minimum conductor size, like on a 225 amp breaker. I can put a 4/0, can't put a 3/0. A 4/0 comes to 230 amps. The breaker is less than that 230 amps. It will protect the circuit. A 250 amp breaker can take 250 kc mill. It's rated for 255. My breaker is less than the 255, except for the 400. 1 500 kc mill. And down here, 7 600s and 13 500s. Those are the 3 instances I have. I can't get a good reason why that is the case. So I do have some discussions going on with a few people from UL and whatnot. But that is where that's at. And then also, I am creating a tool, which once we're done, and this is done, I can share it with you. It's 1 o'clock, so I can be a couple of seconds late. 88 amps. So what I'm doing here is I'm creating, I put in my continuous and non-continuous. So let's say, for example, Control C, Control V. I have 40 amps of continuous and 40 amps of non-continuous. My total load is 80. 125% number of this combination is 90. Terminal 1 temperature rating is 75. 75, the conductor insulation is 90. Number of conductors is 3. So my multiplier is 1. My ambient is 86, so my multiplier is 1. If I put 4 conductors, now I'm 0.8. Now my conditions of use is 100 amps because of that adjustment. My larger of the two is 100. I need a conductor that can handle 100 amps. So if I pick, right now my 90 degree C column is 75 amps. So if I go to a number 4, I'm at 95 amps. If I go to a 3, okay, now I can have 90 degree C is 115. My equipment is 100 amps. I've got my ampacity value of the conductor is 92. Number of conductors in parallel. My total equipment is 100. My total ampacity is 92. I know my breaker has to be at least 100. So if I pick a 100 amp breaker, it tells me I have met all of the conditions. It's not a small conductor. So let's check. A 100 amp breaker with a number 3. 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 Good to go. So I'm creating a spreadsheet that once I get done with this, I'll let you guys have it. You guys can play with it, knowing that, you know, you can always screw it up. But I'm hoping that you don't. So anyway, doing what I can to the journey of understanding ampacity. The next phase of this, we're going to take a look at service conductors and ampacity of service conductors. The next phase will be the motor circuit. Santiago, hopefully you'll be there for that one. All right, everybody, I've got to run. I'm late for my other meeting. So thank you for joining in. Thanks for what you do for electrical safety. Thanks for what you do for the electrical industry. Remember to stay safe and please stay healthy. See you next week.